Hi everyone. In this video we are going to order molecules in increasing acidity or basicity by looking at their conjugate counterparts and also looking at the Ka's and the Kb's of their conjugate counterparts. I know that was a little bit confusing. Let me show you what I mean. If we have a reaction that is HA, I need to give this a title. Oh, why don't I just call this trends? And then we're going to apply these trends in the next sections. If we have a acid HA plus H2O, and let's make this a strong acid. So we'll put a full arrow, and I'm going to say if a strong acid. We're going to get close to 100% dissociation. By the way, I may not have mentioned this in the previous video, or in any video, but dissociation is the same. We're going to think of it as the same as ionization. So 100% dissociation means 100% ionization. And we get the hydronium and the anion. If this is a strong acid, what that implies is that it does not go backwards. So I'll put an X here. But also, what does it imply about this conjugate base? So this is the conjugate base. It implies that if you can't go back, you can't reverse this. It implies that this is not a very strong base. So this conjugate base is implied that it's weak relative to other A minuses that we'll compare to later. But in general, you could say that it's a weak base. All right. Believe it or not, I think we're ready to list some trends. The first trend is, I'll put these as bullet points. Before I go on, let me give this a better title. Trends of the conjugates. How about that? Okay. This is our first trend. We see strong acid. Simply, strong acids result in weak conjugate bases. What's wrong with my spelling? Meaning that A minus does not act like a strong base. Well, the corollary is true. Weak acids result in strong conjugate bases. This doesn't always align with our memorization of the 7 strong acids and the 8 strong bases. You'll see later what I mean by weak and strong is in comparison to other molecules in a set. So really what I could say is the stronger acid results in the weaker conjugate base, or the weaker acid results in the stronger conjugate base. Don't worry, when we do a couple of examples, this will all be pretty obvious. Well, we could look at it from the base point of view. Strong bases result in weak conjugate acids and, of course, weak bases. For the most part, we are going to identify strong and weak acids and bases using the Kas and the Kbs. We'll get practice using those equilibrium constants. Weak bases result in strong conjugate acids. Okay, why don't we just jump into a problem? Oh, before I do that, so what's we're going to notice is that Ka values and it depends what order you're watching these videos in, but if you know what a pKa is, pKa values will be useful. For those of you who remember, pKa is just simply the negative log, just like POH or pH is the negative log of the H plus concentration. Okay, now we're ready for a couple of examples. Part B. Which is a stronger base? Or which is, I should say, the strongest base? We're going to have three choices. Your choices are OH minus, H2O, or NH3. Which is the strongest base? And this is going to be based on Kas. Okay. Probably I'm also going to ask which is the weakest. Okay, now we're ready. If we're using these trends, the strongest base right here is coming from the weakest acid. And we are using, I said we're going to use Kas, so we need the acids to match up with the Kas. When you're doing this problem, take the time to make sure you know which species are the bases that you have to order from maybe strongest to weakest, and which species are the conjugate acids. We need the conjugate acids. Okay, so maybe we should be looking at, I mean, it doesn't matter if we look at that trend, but maybe it's this trend. Strong bases result in weak conjugate acids. What that means is we should be drawing the conjugate acids and finding their pKa's. Okay, this is how I would solve it. Each of these acts like a base, picks up a proton, and becomes, as you know, the conjugate acid. NH4 plus, and these are your conjugates. I already looked up the Ka's for us, and these are the Ka values. For water, oh, I hope I looked it up. Okay, here, for water, it's 1.7 times 10 to the minus 16. That is actually not such a high Ka, so this is fairly weak. What about H3O plus? H3O plus is 5.55 times 10 to the 1. Interesting. So it's greater than 1. NH4 plus, and that's the one I did not pick up. Let me try to find it. Oh, there it is. Nope. Oh man. Let me look that up on my phone real quick. What is that called? That's called ammonium. What do you notice actually? We are not looking up the Ka for ammonia, right? You have to look up the Ka for the conjugate acid. I hope I can find it fast. There it is. 5.6 times 10 to the minus 10. Okay. So just make sure you know which ones go to which. It is a lot of, well, not a lot, but it is a bit of work, stepwise work, to get to our answer, which is the strongest base. The strongest base results in the weakest conjugate acid. So the weakest acid is this one. So here's my analysis. This is the weakest acid. Therefore, this is the strongest base out of these three. You see how that works? Okay, now we're off and running, because now that we have the Kas, we could find the strongest acid. The strongest acid looks like this one, the one that's greater than 1. This is the strongest acid. And therefore, this is the weakest base out of these three. In order of basicity, maybe you could write something like this. OH minus greater than NH3 greater than H2O. And this is, again, basicity. That would be your order in decreasing, right? Decreasing basicity. You ready to try another one? Obviously, if I were to ask this on an exam, I would either have to give you a table of Kas or give them to you in the problem. The trick is, just because you see a Ka for NH3, you're not using the Ka for NH3. You're using the Kas for the conjugate acid, so you're using it for NH4. NH4. Okay. That is asking which is the strongest base. Let me see what I have for letter C. One more. But instead of using Kas, we're going to use our knowledge of what are the 7 strongest acids, or 7 strong acids that we should memorize. Part C. Which is a stronger base? F minus or B minus? Br minus. Which is a stronger base? Is it going to be F minus or Br minus? And we're going to use our previous trends that we've learned about hydrogen halides. Hydrogen halide. Okay, again, do this stepwise. You have your base that you're comparing, F minus versus Br minus, and go ahead and do the work. Don't take any shortcuts with this because it's very easy to get turned around and look up the wrong Kas. But in this case, it's kind of easy to reverse the trend by accident. So here we have HF. You have HBr because we are drawing again the conjugate acids. We're looking for the stronger base, which means we need the weaker acid. Well, we know from our 7 strong acids, HBr is one of them, but not HF. So this is a stronger acid, and this is the weaker base. Okay, and then obviously this is the stronger base. Again, you're not comparing this to all 3 of these. You're comparing it to just Br minus. Those are the bases, and those are your acids. Stronger base. So, what about this? If I give us a reaction HBr plus F minus, equilibrium arrow goes to Br minus plus HF. Do you know which side is favored? Do you know which side is favored? This is a stronger acid. Yes, stronger acid. But let's take a look from the base point of view. This is the stronger base. So these are strong acid, stronger base, and where are the weaker ones? This is the weaker base. The weaker acid. Equilibrium will go in the direction where the reaction wants to take place. These are strong, so that species wants to give up its proton. This F minus wants to accept a proton very strongly. Your equilibrium arrow is mostly to the right. So we haven't really drawn in this unit a lot of unequal arrows like this. Or you could just say, this is what we have done this in the past, favors the products. You'll learn this a lot in organic chemistry, but we might as well sum up this trend. Equilibrium, in an acid-base reaction, equilibrium favors the weaker acid and the weaker base. They are going to be on the same side, guaranteed. So in acid-base reactions, equilibrium, and that makes sense, right? Since these are weak, that Br is less likely to grab this proton because it's a weak base. And this HF acid is less likely to give up its proton than HBr because it's the weaker acid. So it will not really go, it won't favor the reverse direction. You see how it favors the products. And for the bullet point, in acid-base reactions, equilibrium favors the weaker side. Honestly, I always say the weaker acid. But you could also say the weaker side or the weaker acid base. Okay. I have one last. Oop, I do. Letter D. Stronger acids. So we've been looking and identifying the stronger and the strongest bases. How about order? Order in increasing acidity. And we're going to use KBs now. Okay, so I have a list of KBs that I'm going to give you, but I'm interested in H2CO3. Okay, so that's an acid, but when it loses a proton, you make a molecule that's still also an acid because it has that proton to lose. Let's NH4 plus and HPO4 2 minus. Okay. Again, don't take shortcuts for this because there's a really simple step-by-step way to do these problems. You don't want to lose points just because you are rushing or you are taking shortcuts. We want to draw what? So in this case, we actually want to draw the conjugate base. And those are the species or the molecules that I'm going to give you the KB for. Okay. H2CO3. Oh, I have to write the conjugate bases first. HCO3 minus. You want to fill in the rest, and while you do that, I will give us the KBs. Okay, let me figure out which is the strongest conjugate base. I got it. All right, so let's fill in the conjugate bases. H2CO3. Also focus on the charges. NH4 plus loses a proton and goes back to neutral, and H3 HPO4 2 minus gains a proton to become H2 PO4 1 minus, or just minus. Did I do that right? I did not do that right for some of these. Hopefully you did this ahead of time and also caught my mistakes. We gotta draw the conjugate bases. What am I doing? You have to lose a proton. So that's good. Good practice. You're negative, and then when you lose a proton, you get more negative by a -1 charge. That one's good, but this one's no good. Right? We have to lose that proton. Now this becomes 3 minus. Okay, we're good now. Order in increasing acidity. Go ahead and take a shot at it while I think. Okay, I want to start with the molecule that has the lowest acidity, because we're going to fill in the greater sign like this. And the lowest, the weakest acid comes from the strongest base. The strongest base is right here. And so I'm going to put here HPO4 2 minus is the weakest acid. Next is, so next is this one. We'll call this number 2. HCO3 minus, followed by NH4 plus, very interesting, followed by H2CO3. This is your strongest acid, right? Because it is the weakest conjugate base. A little bit surprising, because we do have a species that is positive, and typically when something is a charge like that, if you can lose a proton to get back to neutrality, a neutral molecule, it tends to happen pretty readily. But carbonic acid is a fairly strong acid, stronger than NH4 plus, based on, again, the KBs of the conjugate bases. And this one is the weakest. It really doesn't want to lose another proton to become 3 minus. Most cases, the more charge you put on a molecule, the more unstable it becomes. Alright, that's the order from weakest to strongest, and we are following the directions. Order in increasing acidity.